Okay. Hi, everyone. Hello, everyone. Happy to have you here. I finally have kind of a bit of a starting screen, so that's very exciting. I need to add some music or something to it. But for now, that's exciting. Anyway, welcome back. It's time for class. Yeah, welcome. I'm glad you're on time this time. Though, of course, it's okay if you're a little late. I totally get it. Life happens, or if you need to leave early and that kind of thing. I'm an understanding person, I like to think. Uh, you know, Life doesn't pause for education. Anyway, today we are starting on one sample t-test. So we're starting to use statistical tests that I actually use for hypothesis testing. Oh, hello! Welcome. Happy to have you here. Don't you make sure you're getting enough sleep, okay? Like the VOD will be there if you need to go to sleep. Don't worry about it. Is the starting soon? Yeah. I set it up literally like 2 minutes before the start of the stream. I've had the GIF for a while, but I haven't really done anything with it yet. So thank you. I'm really glad that you like it. All right. Today we are talking about one sample t-test. Sleep is for after graduation. Sleep seems to be a very important part of memory formation, so make sure that you're getting sleep, and that will help the learning process, I hope. All right, let's do this. Let's talk one sample t-test today. So previously, we had talked about something called the standard error of the mean. This was the standard deviation of a distribution of sample means, or means in general. And it's a numeric estimate of sampling error. I legit slept 11 hours after my last exam of the semester. I, I have been on weekends between class weeks. I've been sleeping 10, 11 hours, so I feel you on that. Sleep is so important, and I am doing my best to get a lot of it. And maybe getting more of it than I probably strictly should. But that's better than the opposite, right? Anyway, yes. So standard error of the mean. This is a number that represents our sampling error. It is on average how far we expect a sample mean to be from the population mean. And the formula that we had for that was this. The standard error of the mean, which is represented as sigma sub m, is equal to the standard deviation of the population divided by the number of people in each sample that you're working with. Then we also learned about the z-test and the z-score. So here is the z-test specifically. This is comparing a sample mean to a population mean. And it's calculated as the sample mean minus the population mean over the standard error. So it's how far away your sample mean is from the population mean in units of standard error. Pretty handy. We talked about hypothesis testing. We compared one person to a population with z-scores. That was the x minus score minus the population mean over the standard deviation. We compared a group of people to a population mean with the z-tests. That was the one that I just showed you, that formula with the sample mean minus the population mean over the standard error. Whew. And both of these tests had sort of like this feature, I guess you could say. Both of them had population data. They assumed that we had the population mean and also that we had the population standard deviation. But if you're familiar with the real world and anything that involves collecting data, the population is every single individual or every single thing in the group that you're interested in, the population that you're interested in. With psychology, sometimes that might be every single human being ever, or every single human being that's currently alive, or every single first-generation college student, every single person who watches YouTube on a regular basis, every single person who's ever played a certain video game. Like, it's not realistic to assume that you have population information. A lot of the time, we do not have any population information whatsoever. So we usually can't do a z-score or a z-test for hypothesis testing. That's not something that we usually have enough information to do. So I'm going to start out slow. I'm not going to take away all of our population information right away. For now, I'm gonna take away our population standard deviation, because most of the time we just don't have that information. That's not a thing that we have. We do not have a population standard deviation. This is super common. This is way more often than not. So now we've got to do something new. Before, We had this information, so we could just do a z-test, and that was great. Now we don't. We can no longer just do a z-test, so now we've got to do something else. Which is where, well, the t-statistic comes in. We do not have the population standard deviation anymore. We don't have that information. So we're going to have to estimate it. We don't have population information, but we can still try and estimate what the population variability is, what the population standard deviation is, and that's what we're going to do. The way that we're going to do this is we are going to use our sample standard deviation to estimate it. The sample isn't our whole population. That's kind of the point of a sample. It's only a small subset of your population, but it's still part of the population. You have some data. You may not have the population data, but you have something, and that's better than nothing. And it's part of the population, so we can use that to estimate the population standard deviation. Of course, we kind of touched on this a little bit last time, and then probably the time before that. We know that the variability in a sample, whether that's the variance or the standard deviation, is going to be, usually, it's going to underestimate the true variance in the population. We know that if we just like normally calculate the sample standard deviation without making any adjustments to the population formula, we're going to get a number that's just like a little too low. We're going to underestimate it. This is what we call a biased statistic. We know it's getting something wrong, and it's consistently getting it wrong in the same way. It's consistently underestimating the true value. So up until this point, we had population data, and we were using these formulas. We have this formula for the variance on top, the sum of each score minus the sample mean squared over the number of people in the sample. Or you could also think of this as the population if you're using data for the whole population. The standard deviation was just the variance formula with a square root. So this is the formula that we've been using so far. These are the formulas we've been using so far, but both of these formulas assume that you have population data. They're not dealing with the fact that we know sample data will underestimate the variance and standard deviation pretty consistently. So that means we've got a new measurement. And I've already kind of shown you this formula at one point or another, but this is S. So up until now, we've been representing the population standard deviation. It looks like I don't have it. With the Greek letter sigma. We've been using this so far. This is specifically for the population standard deviation. Typically speaking, in statistics, at least with the notation that I'm used to using, we use Greek letters for population parameters. But now we're not working with population data. So now to refer to the sample standard deviation, we're going to use the letter S, lowercase s. S is a measure of standard deviation that corrects for the problem with using the population standard deviation on a sample. It says we know that this would be an underestimate if we're not careful. So S has made a correction to the formula to make sure that we're not underestimating the population standard deviation consistently. These are our new formulas for standard deviation and variance. Come on. Come on, PowerPoint. There we go. Okay, so this one on top, this is the variance. So our old symbol for variance in the population was this. Now instead of sigma, we've replaced that with S to indicate this is sample variance, not population variance. And the same is true for the standard deviation. We've replaced the just sigma for the population standard deviation with S for sample standard deviation. The main difference between the population formula and the sample formula is that we have this on the bottom. PowerPoint just needs some encouragement sometimes. Yes, this is very true. It keeps forgetting that I'm trying to change the slide, and it's like, I don't feel like it. And you just got to give it some gentle encouragement from time to time. But it's a pretty nice program. So yeah, we have changed the denominator. Before, on the bottom of these formulas, we just had the sample size. Now we've changed that to the sample size -1. That is the difference between the population formula and the sample formula. Everything else is pretty much the same. We've changed the notation a little bit to indicate we're working with samples instead of populations, but the only mathematical difference is changing the sample size as the denominator to the sample size -1 for the denominator. Not a huge change, but it is a change. Come on, PowerPoint. Okay. There's also a shorter way of writing this, by the way. You might see me do this sometimes because I'm a little lazy when it comes to writing, and also, I don't want to take too long while I'm writing. This whole formula, the sum of x minus m squared, that is called the sum of squares. So you can just also abbreviate that as just SS. This SS here stands for this whole big long thing. And this n minus 1 here is called the degrees of freedom. So I can abbreviate this sum of x minus m squared over n minus 1 to just the sum of squares over the degrees of freedom. And the same is true for the standard deviation formula. I can just abbreviate that as the square root of the sum of squares over the degrees of freedom. The denominator is now smaller, so rather than just having n, our sample size, it's n minus 1. So the denominator is smaller now. And because the denominator of the fraction has become smaller, when you make the denominator of a fraction smaller, assuming everything else is the same, you make the end result bigger. It becomes a bigger number. You're dividing it by a smaller number, the output's a bigger number. This helps us compensate for the fact that the population standard deviation would consistently underestimate, that the formula for the population standard deviation would consistently underestimate the true population standard deviation if you're using it on a sample. So this is our fix. We know that the population standard deviation formula will give you a number that's too low if you use it on a sample. This adjusts for that. This just says, okay, we're just going to make it a little bigger, and therefore we're no longer underestimating as much. And yeah, that n minus 1 at the bottom, it does have a special name. That name is the degrees of freedom, also abbreviated as DF. I know I already said that verbally, but it's nice to have it on the slides, right? So we have changed how we are calculating our standard deviation and variance. We don't have the population standard deviation and variance anymore, but that's okay, because we can estimate it using this formula, just using our sample data. The technical name for this is the estimated standard error, or is the estimated standard deviation and variance, and we can use these to calculate the estimated standard error. The notation for the estimated standard errors changed pretty much the same way the notation for the standard deviation and the variance did. We've replaced sigma with m. So before it was written as sigma of m, this was the population standard error. Now we've written it as S of m. That's our sample standard error. And it's just an estimate of the real, it's an estimate of the population standard error based on a sample. If you don't know the population standard deviation, which was required to calculate the population standard error, then you just replace the population standard deviation with your best estimate of the population standard error. In other words, your sample standard deviation. So this is our new formula for calculating the standard error. Standard deviation divided by the square root of the sample size. The only difference is that I've switched from the population standard deviation to my best estimate of the population standard deviation. That's the only difference. It really has not changed that much at all. Well, like barely at all. Now, in the formulas for the standard deviation and the variance, we did have that degrees of freedom on the bottom, but you'll notice that we don't have a degrees of freedom on the bottom of our new standard error formula. We don't need to, because we already corrected for that bias when we calculated our estimated standard deviation. We already did that small correction. We don't need to do it again. This is already corrected, so it's already factored into this. We don't need to use the degrees of freedom again here. Nice and handy. Saves us some work. I like it when we can save ourselves some work. All right. How we doing, by the way? I hope everything's making sense. Feel free to chime in chat if you're ever confused or like you need clarification or you just have some curiosities and that kind of thing. I'm happy to take questions at any point. We do not have a limited amount of time for this class. There is no worry about reserving the classroom, so seems good? Awesome, I'm glad to hear it. Yeah, in real life, if this was an in-person class, we would have to worry about like the next professor coming in and like staring at us awkwardly, waiting for us to evacuate the classroom so they can start their class. But here we don't need to worry about that. So that is very nice. All right. So this leads us to something called the t-statistic. Remember the z-test from before? Now we're doing t-tests. Z-tests use the z-score, which was a z-statistic, you can call it that. Now we're using a t-statistic for a t-test. The t-statistic is used when you don't have population information. You can use it if you know the population mean, But assuming you're at least missing the population standard deviation, you can use a t-test, and you can also use a t-test if you have zero population information whatsoever. The simplest version of the t-test, and the one that we're going to be focusing on today, is the one sample t-test, which is written, the formula for that is written down below, right here. This is the one sample t-test formula. It is a sample mean minus the population mean, and this doesn't actually have to be the population mean. I think I have a slide for that later on, but something like that, over the standard error. This should look very, very similar to the z-test formula. The z-test formula was z is equal to a sample mean minus the population mean over the population standard error. The only thing that we've changed from the z-test to the one sample t is we're not using the population standard error because we can't calculate it. We don't have population data for the standard deviation. We've replaced it with our estimation of the population standard error, our sample standard error. That's the only thing that we've changed. It's super similar. Now for z-tests, if we knew the standard error, if we had the population standard error, we could just calculate a z-score, compare it to the z-table, and we'd be good. But now we don't have that information. That only worked if we had both the population mean and the population standard deviation. Now we don't have that anymore, so we can't do that anymore. For t-tests, we might have the population mean if we're doing a one sample t-test, but we definitely don't have the population standard deviation. We have an estimate of it, and an estimate is a heck of a lot better than nothing, but we don't have the actual population standard deviation. Now, we do have an estimate, but that estimate's accuracy is going to depend on our sample size. The bigger your sample size, the more accurate of a picture of the population you have. The smaller your sample size, the less accurate you have. You can think of it like, let's say, if my population is 1,000 people, let's say there's 1,000 people in whatever group I'm studying, I'm probably not going to get a very accurate picture of what those thousands people are like if I only get data from 5 of those people. That's probably not giving me an accurate picture. I probably can't make a super accurate estimate about the population mean or standard deviation. But if I up my sample size to 900 out of 1,000, I have 90% of the population. That probably gives me a much better picture of what's going on there, and my estimate is probably going to be a lot better. So we know the accuracy of our estimate of the standard deviation is going to depend on the size of our sample. Bigger samples will lead us to a more accurate estimate. Smaller samples are going to be a less accurate estimate. So because we're estimating, we want to take into account our sample size when doing our test, because we know a bigger sample size gives us more reliable, more accurate results, and a smaller sample size is probably going to result in less reliable, less accurate results. So we want to account for that. We didn't have to account for that with z-test because we had the entire population, but since now we don't, we do need to start worrying about that. The t-distribution is what we're going to be using. So before we were looking up z-values on the z-distribution. That's that whole z-table thing where we're looking up probabilities and stuff. The t-distribution is what we use for t-tests, and it's really similar to the z-distribution. It's also a fairly normal, it's not like a perfectly normal distribution, but it is symmetrical and unimodal. So it looks very similar to a z-distribution, or the z-distribution. But unlike the z-distribution, it takes into account how many people your data comes from, the size of your sample. There's not actually just one z-distribution, or t-distribution. There was one z-distribution, but there's not just one t-distribution. There's actually like a theoretically infinite number of t-distributions, one for every possible degrees of freedom, which you can also think of as like one for every possible sample size. There's a different t-distribution if you have a sample size of 3 versus 10 versus 35 versus 3,502. Every possible sample size has a different t-distribution. So it's more like a series of distributions or a collection of distributions than just one single be-all, end-all. This means that every time you do a t-test, you need to determine a critical value because your distribution has changed. Before, it was just, is the z-value further from 0 than plus or minus 1.96? Congratulations, it's significant. Now we can't rely on that 1.96 anymore. We cannot use that as our cutoff anymore. Our cutoff is going to change depending on our sample size and depending on our degrees of freedom. Now, normally this would mean doing calculus. I don't know calculus. Some of you might know calculus, and in which case, good for you! But I don't. But luckily, statisticians have created tables that can tell us the critical value that we're looking for. Yay, calculus! I'm scared of calculus. I'm not... I mean, it's okay. I'm sorry. Yeah, we're not doing calculus. Other people have done the calculus for us, so we don't have to do calculus. I know this may be disappointing for some of you, but maybe others of you will be relieved, like me. I'm relieved that we don't have to do calculus. They made me take 3 levels of calculus. Oh no. I'm sorry. I never took any. I escaped with my life. Oh, I'm blocking some stuff. I'm gonna have to start peeking up from here again. Hi. So yeah, luckily, statisticians were very kind to us and they made it so we don't have to do calculus. They have created tables where we can look up the cutoff for common alpha levels, like alpha of 0.05, which is most common in psychology, for a bunch of different degrees of freedom. And also, like, if you're in more advanced statistics, you're, like, doing statistics with a statistical program like R or SAS or SPSS or MATLAB or whatever, those will actually calculate the critical value for you as well. So you don't even need a table, much less calculus. The program will do it for you, which is nice. One day, I'll start a series of R tutorials. I would like to do that as well. But for now, let's at least get the basics of stats down. So this table, on this next slide, this is the t-distribution. And we could use this to figure out our cutoff. Because there's a lot more that we have to do here, there's an infinite number of t-distributions. The z-distribution could deal with basically like any alpha level we wanted. We could use the z-table for. We can't do that anymore because we've got a whole bunch of different distributions, not just one. So this allows us to figure out our cutoff for an alpha of 0.05, 0.01, or 0.0, like it's got a couple different alpha levels in there, but based on our sample size, we can figure out our cutoff, our critical value, the value that we need to beat to reject the null. It does this by looking at your degrees of freedom. So in this case, you need to know your degrees of freedom before you go in. So let's say I have a sample size of 16 participants or 16 observations. My degrees of freedom, just to remind you of the formula, is your sample size minus 1. So if I have 16 participants and my degrees of freedom is my sample size minus 1, what is my degrees of freedom? Sorry, my hair keeps falling in my face, which makes my eyes do weird things. Yeah, sample size is 16. Degrees of freedom is sample size minus 1. What is our degrees of freedom? Yes, 15. Good job. Yep, there it is. Our degrees of freedom is 15. Our degrees of freedom determines which row of the t-table we're in. So let me show you how this works. I have a zoomed in version of this too, by the way. I'm going to show you really zoomed out right now, but the rows, the row that you're in is determined by your degrees of freedom. So our degrees of freedom is 15. We go down to the row that's labeled 15. The columns are different alpha levels. So we have a column for an alpha level of 0.5, 0.2, 0.1, 0.05, 0.01, and 0.001, I think. The fourth column is 0.05, which is the standard alpha level in psychology. And you look where the row for your degrees of freedom and the column for your alpha level meet, that's going to be your new cutoff. In this case, our critical value is plus or minus 0.2131, or 2.131. It's no longer 1.96, it's 2.131. And I've got a slide for that red line down there, but just to zoom in, here we go. You can see the rows are labeled degrees of freedom. You scroll down, ours is 15, our degrees of freedom is 15, so we go down to the row that says 15, whoop, right there. Then we go to the column where the proportion and two tails combined. We're doing a two-tailed test. Two-tailed test is the standard in psychology, like we talked about on Tuesday. Or Monday, sorry. We go to the column that says two tails combined, 0.05, because that's our alpha level. We find where they meet. They meet at 2.131. That is our cutoff. So instead of having to be beyond plus or minus 1.96, now we have to be beyond plus or minus 2.131 to reject the null. Now let's go to the bottom of the table. There's something I want you to notice. The last row of this t-table that I'm showing you is infinity. This is basically like an infinitely big sample size. And at that point, let's go back to this column. This fourth column here is our alpha of 0.05. By the time you have an alpha of 0.05 and a theoretically like infinitely big sample size, your cutoff goes back to plus or minus 1.96. At that point, you basically have the population. You're basically back to doing a z-test. Generally speaking, you can see as your sample size and therefore your degrees of freedom increases, the number that you have to beat to reject the null decreases. You can see when your sample size, when your degrees of freedom is only 2, let's say you have 3 participants, the number that you need to beat to reject the null is 4.303. But as you increase your sample size, the number that you need to beat to reject the null gets smaller and smaller because you're becoming more and more confident that your results are accurate. So you don't need to keep your standards as high. You're closer and closer to the population. You're getting closer and closer to a z-test. So you don't need to set your standards quite as high because you can be a bit more confident in the results. Bigger your sample size, the lower your cutoff, basically. All right, let's get to our steps of hypothesis testing. We're using the same 6 steps of hypothesis testing that we went over last time, but I'm modifying some of them. The ones that I'm modifying are highlighted in red. So we're still stating our null and alternative hypotheses pretty much exactly the same way that we were before. That has not changed. When we get to step 2, though, we have to worry a bit more about our comparison distribution. Before, I was just telling you this is the population mean, this is the population standard deviation. I'm still going to give you the population mean for now, for one sample t-test, but now we no longer have the population standard deviation. We're going to have to estimate it, so that becomes part of this step. Rather than just me telling you the population standard deviation, we're going to have to figure that out, and then we're going to have to use that to estimate the population, or to get our estimated standard error. And then we also calculate degrees of freedom at this step. So now we actually have to do a bit of extra work here. Rather than just me giving you everything, now you have to do some calculations. Step 3, before we just said our cutoff is plus or minus 1.96. That gives us a 5% chance of a type 1 error. But with the t-distribution, now we actually have to look up what cutoff gives us that 5% chance of a type 1 error. So at this case, you have to look up your t-critical value. You have to look up your critical value rather than just assume it's plus or minus 1.96, using your degrees of freedom, your alpha level, and whether it's a 1 or 2-tailed test. In psychology, again, your alpha level is almost always 0.05, and you're almost always doing a 2-tailed test. So really, the main thing that you need to know is your degrees of freedom here, assuming that you're following standard psychology statistical practices. Alpha is probably determined for you at 0.05. Test is probably determined for you at 2-tailed. Then for step 4, I'm adjusting that a little bit. We're no longer using the z-test formula, we're using the t-test formula. Step 5 is still the same though. You're still making a decision. You're still comparing the number that you get out of, whoa, sorry for the sirens. Hopefully you can't hear that, but they're coming closer. Anyway, we're going to power through it. Okay. So, step 5, we're still making a decision the same way. You compare the number that you get in step 4 to the cutoff you set in step 3. Yeah, it's sirens. It's sirens. Sorry. You can hear it a little. Yeah, I need to get better soundproofing, but we do get sirens around where I'm streaming from semi-often. Hopefully it's okay. Hopefully it's nothing bad. Hopefully it's just a false alarm. Anyway. And then step 6, you interpret your results. Same old, same old. You interpret them the same way. You can't hear it. Yeah, they're out of my hearing now as well. So they're out of range. All right. So let's do an example. Let's do an example of a one sample t-test. They heard someone was p-hacking. I'm not p-hacking right now. I could teach you how to p-hack if you want. We won't be doing that today, but I'm happy to teach you how to p-hack. I would do it, and then I'd tell you don't do this. But, anyway. That would be funny, though. Imagine, like, calling the police. Excuse me, police, somebody is p-hacking. And the police would be like, what the hell does that mean? And just like, they're messing with their statistical analysis to ensure they get a significant result, but really they're placing themselves at a higher risk of type 1 error. And the police are just like, I'm hanging up now. That would be very funny. I'm not gonna lie. Maybe it would only be funny to me and, like, stats people. I don't know. P-hacking for fun and profit. Not that there's much profit in p-hacking, unless you try really, really hard. But anyway, okay, our example. This time I'm going Haikyuu. Haikyuu, the volleyball anime. Well, it's not the only volleyball anime, I don't think, but it's my personal favorite, and to my knowledge, the most popular one. Anyway, let's say I'm Coach Ukai from Haikyuu. He is the coach of the protagonist volleyball team. I want to know if the players on my volleyball team, Karasuno, which is the protagonist volleyball team in Haikyuu, are scoring more points per game than the average player in their league. Let's say I know that the average player in their league scores 8 points per game, and I actually did some Googling. It seems like the average number of points scored per game per player is 8 points in volleyball. I don't know if the source I got that from was good, though, so take that with a grain of salt. So let's say the average player in the league is scoring 8 points per game. My team, Karasuno, has 12 players, and I know that my 12 players score an average of 10 points per game. So I want to figure out if my team is, like, if my average player is scoring more points per game than the average player in the league. That's my goal. Unfortunately, I do not know the standard deviation of average points per player, and this is kind of common. Like, if some organization or something does report the population mean for something, they don't often report population standard deviation or something like that. They just kind of assume most people won't know what to do with that. So usually they only report the mean if they report anything. So fairly common situation, I would say. So let's go through our steps of hypothesis testing. Step 1, we have to state our hypotheses, our null and our research hypothesis. Our population 1, this is Karasuno's players, my volleyball team, and population 2 is all the other players in the league who I'm comparing my team to. My null hypothesis, of course, is that nothing's happening here. There is zero difference in how many points my players score in an average game compared to the average player in the league. Everything's the same. The average points scored in population 1 and population 2 are the same. The mean of Karasuno players is statistically indistinguishable from 8 points per game. The alternative or research hypothesis, of course, is that there is a difference. My players do score a different amount of points than average. So the mean of Karasuno players' points scored is different from the mean of the general league points scored. The mean of Karasuno players' points scored per game is not equal to 8, which is the population mean. So there's my hypotheses. Null hypothesis, there's no difference. My players score an equal, well, statistically, there's no significant difference in how many points my players score per game compared to the general player in the league. Alternative hypothesis, there is a difference. All right, step 2, we've got to state what is known about our comparison distribution. Describe a world where the null is true, where there is no difference. Well, first, our comparison group, the league at large, has a population mean of 8 points scored per game. So that's step 1. I've just given you the population mean. Step 2, we need to determine the degrees of freedom. My team, Karasuno, has 12 players. The degrees of freedom is your sample size minus 1. So 12 minus 1, my degrees of freedom is 11. Pretty easy. 11 degrees of freedom here. Then we have to calculate the freaking sample standard deviation, which is a long and tedious process. So I have it animated out here, but let's say these are the average points scored per game for all 12 of the players on my team. The formula for our sample standard deviation is the square root of the sum of squares, so the sum of x a given score minus the sample mean over, or squared, over my degrees of freedom. So my first thing here is, do I have the X values? Yeah, I have all 12 of my scores. Do I have my sample mean? Not yet. So your first step is to calculate the sample mean. That means add up all 12 of these scores and divide by 12. And that would give you 10. The average, as I said before, the average number of points scored by my team, or by players on my team per game is 10. Then now we can do this X minus M. We can do the parentheses. We can see how far each score is from the mean. So for the first one, I do 8 minus 10. It is 2 points below the mean. 14 minus 10, that's 4 points above the mean, and so on and so forth. You go all the way to, I've already gone over how to do this, but it's tedious, so I'm just going to kind of like speed through it a little bit. Once I've got all the deviation scores, how far each player's points are from the average, then I'm going to square those deviation scores. So -2 squared is 4. 4 squared is 16, 4 squared is 15, or 16, -5 squared is 25, yada yada. I get all my squared deviations from the mean, so that's this squarey bit. And now the final part for the numerator of this equation is just, I've got to add up all those squared deviations. I got to add all these together to get my sum of squares. So I add those 12 squared deviations together to get a sum of squares of 170. The top of this formula is 170. So sorry, I sped through that. I've been over how to do it before. It's mostly just tedious bunch of math. Here's our formulas. So we can start plugging this stuff in. We know we just calculated the sum of squares is 170, so that goes up here. The numerator is our sample size minus 1. We have 12 players, so that's 12 minus 1. So we calculate 170 over 12 minus 1 is equal to 170 divided by 11. You calculate 170 divided by 11, take the square root, and we're going to end up with an estimated standard deviation of 3.93. I'm sorry, I'm speeding through this. One day I'll do a stream where I'm just like doing a whole bunch of examples of this by hand all the way through. I'm tired. I'm sorry. Now that we have our estimated sample standard deviation, we can plug that into our standard error formula. So our standard error formula has the sample standard deviation on top. So we put 3.93 divided by the square root of our sample size, which was 12. So I do have this typed out so you don't have to deal with my horrible, horrible handwriting. So that's 3.93 over the square root of 12. First you square root 12, then you do 3.93 divided by that square root of 12. Your standard error is 1.13. Step 2 is now done. I have established that the population mean is 8. I gave you that information. And then we used that, we calculated our degrees of freedom. 12 players minus 1 is 11 degrees of freedom. And then finally, we estimated our standard error, which ended up being 1.13. So now we have our estimate of sampling error. Our comparison distribution has a mean of 8 and a standard error of 1.13. There we go. Now we can move on to step 3. We've got to set our cutoff. We've got to set how far away from the population mean is far enough for us to conclude that my players are built different than the average player in the league. So we need our degrees of freedom here. Our degrees of freedom are 11. This determines which row of the t-table we're in. We're going to go to the row of the t-table that is labeled 11. We are, of course, using the psychology standard of alpha of 0.05 with a two-tailed test. The proportion of two tails combined, 0.05, that is the fourth column on your t-table. You look at where that row and that column meets. So zooming in a bit, row 11 for 11 degrees of freedom. Column 4 for proportion of two tails combined, 0.05. And where those meet is 2.201. That is our cutoff. Our t-score, the result of our t-test, needs to be further from 0 than 2.201, either positive or negative, for us to reject the null and say my players have a different average points scored per game than the general league at large. So yeah, there's my critical value, plus or minus 2.101. Instead of plus or minus 1.96, now we're plus or minus 2.101. or 2.201, sorry. Our standards are a bit higher because we're using a sample instead of the population. So we got to be a bit more careful about rejecting the null. So I've made it a little harder by, making my critical value a little higher. Now step 4, we calculate our t-test. First things first, my sample mean was 10. On average, my players scored 10 points a game. The population mean was 8. On average, players in the league scored 8 points. The standard error that we calculated was something that I don't have memorized, so let's go back and check. 1.13. This is the standard error we calculated. It was 1.13. So our standard error was 1.13. And that's the main information that we need to calculate our t-test. So here's our formula. It is the sample mean minus the population mean divided by our estimated standard error. Our sample mean was 10, minus the population mean of 8, over our standard error of 1.13. 10 minus 8 is 2, divided by 1.13. And I don't know what that is off the top of my head, but you know what? I bet I could use a calculator to figure that out, and no one will stop me. 2 divided by 1.13 is about 1.77. Yep, there we go. I had it animated out here, just so you don't have to deal with my nasty handwriting. Yeah, 1.796. Or is it I have 1.769 on my calculator that I rounded to 1.77. Yeah, so something like that. 1.7 something. It got the last 2 digits. Yeah, the transpose the digits. I do that kind of thing all the time. But yeah, our t-value is 1.77. My team's players scored 1.77 standard errors above the population mean. This might also be a good time to calculate our effect size. Last time we talked briefly about Cohen's d, which was a form of effect size. We'll talk more about it later in this lecture. But the formula I gave you last time assumed we knew the population standard deviation, but we don't know that anymore. So we're going to change the formula the same way we did with the t formula. We're going to swap out the population standard deviation with the estimated standard deviation that we calculated way up where's. We calculated that when we calculated our standard error. So that was 3.93. Our standard deviation's 3.93. So I can start plugging things in. Standard deviation is 3.93. I like to do this to keep track of all the numbers that I have, because otherwise I'll forget them. So the numerator of the Cohen's d equation is the same as for the t-test. It is your sample mean, which in our case was 10, minus the population mean, which was 8. Divided by, in this case, not the standard error like the t-test, but the standard deviation, 3.93. 10 minus 8 is 2, divided by 3.93, which ends up being some number. I'm going to do it over here. If you want to follow along and do it there, that's fine too. 2 divided by 3.93. I believe our Cohen's d is, rounding to 2 decimal places, 0.51. I believe. Let me erase this bitty and then animate it out, because I do have the answer on the slide. Yeah, 0.51. Now, Cohen's d is technically the name for this effect size when you're using full population data. Technically, if you're using this adjusted formula here, it's technically called Hedges G. Like, the technical name for it is Hedge is G. I have never heard somebody actually call it this. Like, this is the correct name for it, but I have never seen somebody writing a research paper and said, Hedges G was, they always say Cohen's d. So, like, you may never see Hedges G in the wild, but in the case that you do, they're meaning an estimate of Cohen's d. That's what they mean. Usually they'll just straight up say Cohen's d, even if they're not using population information. But, you know, just in case you run into somebody who's actually using the proper name for it, Cohen's d, Hedges G, pretty much the same equation. And most of the time people refer to Hedges G as Cohen's D. So, as if that wasn't confusing enough. But I think it's, assuming they're working with sample data, Hedges G and Cohen's D are the same, assuming they're working with sample data. If they might have some population data, then you might want to check to be sure, but the interpretation of them is the same. So now, step 5, we got to make a decision. The t-value that we calculated was 1.77. The cutoff that we set in step 3 was 2.101. So our cutoff is around here, plus or minus 2.101. We have to be further from 0 than that. Our t-value needs to be further in the tail than 2.101 for us to reject the null. Our t-value was 1.77. It is not in the tail. It is not beyond our cutoff. It is closer to 0 than our cutoff. So in this case, we failed to reject the null. Looks like some good time for some p-hacking. Yeah. How could I p-hack this? I could do a lot of things, actually. I could, not necessarily p-hacking, I could change the type of test I'm doing. I could remove inconvenient data. I could collect additional data. I can bootstrap this if I want. I can do a whole bunch of bootstrapped samples to artificially increase my sample size if I wanted to make this significant, but we're not going to do that. You know, p-hacking is not good practice. So, but you know, if you wanted to reject the null, there are ways. They're not ethical ways. There are ways. Yeah, no, we're not going to be p-hacker here, though. Maybe I can talk about p-hacking one day, but today we're not going to do that. We're going to be good researchers, and we're not going to p-hack today. Tomorrow, who knows? I'm not streaming tomorrow, so you would never find out. Okay. So yeah, we failed to reject the null. It is still too likely that that difference of 2 points scored per game, that difference between the population mean and our sample mean, it's still too likely that that was just a random coincidence, that my 12 players just so happened to have an average that's 2 points above the population mean, and that doesn't actually mean anything. They're not inherently better, or just maybe this season they're kind of having good luck in the game, or they were up against weaker opponents or something like that. We can't conclude that it's anything meaningful. So that's step 5. We made our decision. Step 6, interpret your results in plain language. Whatever language you're communicating in, put it in plain language. So in this case, the number of points that Karasuno's players scored was not significantly different than the number of points the average player in the league scored. Now, when I present this write-up to my students, sometimes they're like, okay, but how would we have written it if we did reject the null? So this is what we found. We did not reject the null here. And this is how you might phrase that. But let's say that hypothetically we did reject the null, or maybe we took Haraday's suggestion and we did a lot of p-hacking and we rejected the null through unsavory means. In that case, we might write it up like the number of points Karasuno players scored was significantly higher than the number of points the average player in the league scores. Because if we had rejected the null, that's what we would have found. Our sample mean was higher than the population mean. We can't say it's meaningfully higher because we didn't reject the null, but if we had rejected the null, at that point I can just interpret this number is bigger, and because I rejected the null, it's significantly bigger, it's meaningfully bigger. Unfortunately, we didn't reject the null, so like our real proper write-up without any p-hacking or shady practice or lying would be like this. We can't say that they're different. Statistically speaking, I don't have enough evidence to say that my players are any better than the average league player, or any worse than the average league player, if you want to frame it in a more positive lens. Now, APA style, the American Psychological Association, APA, has some set rules for how you should report statistics. They have a lot of rules for everything. Like if you've ever done APA style citations or written an APA style paper, they have a lot of that. I have some tutorials on my channel for like writing up a t-test at APA style and creating a correlation table in APA style, by the way, if you're interested, and I can create more of those. But for now, writing up our particular t-test in APA style, the first thing that comes is my sentence. My sentence where I tell people in plain language what I found. People don't need to understand any statistics to understand what I'm saying here. They don't need to know what a t-value is to understand that I didn't find any evidence that Krasno was scoring any more points on average than the general player in the league. I've told them that in plain language. For the people who are interested in statistics, here's how we formatted an APA style, this little numbery bit at the end. By the way, this is a sentence fragment. It's part of the main sentence. It's another clause in the sentence. It is not its own sentence. It's not stand on its own. It's just supporting information for what I just said. First, you put a T. That's indicating you did a t-test and you used the t-distribution. We looked up our critical value in the t-table. Then in parentheses, you put the degrees of freedom. This way, from this alone, if somebody wants to check our critical value, they don't believe us that we properly rejected or failed to reject the null. And they're like, I don't think you set the right critical value. We can say, well, okay, go to the t-table, go to row 11, check alpha 0.05, two-tailed. Now you can look up my critical value. You don't have to trust me on this, bro. You can look it up. I've told you where to look to find out what my critical value was. But they don't have my data, so I am going to have to tell them the t-value that I calculated. So a t-test with 11 degrees of freedom gave us a t-value of 1.77. We failed to reject the null, so our p-value, the probability that we would have randomly selected a sample with this mean if the null was true, is greater than 5%. Technically, APA style tells you to do an exact p-value, so technically I should be like p is equal to point whatever it would be, like 0.231 or something like that. But if you're calculating it by hand, you probably won't be able to get an exact p-value unless you're doing a lot of calculus. I believe the tutorial that I have, the how to write up an APA style t-test video shows you how to do it if you have the exact p-value. And if you go far enough in, psychology and data analysis, you're going to be using a program again like R or SPSS or SAS or MATLAB or Python or something like that to calculate your stats, and they will give you the exact p-value. So normally you wouldn't write p is greater than 0.05. These days you'd put the exact p-value to 3 decimal places. If you're reading an older paper, like a paper that was published in like the early 2000s, the 90s, the 80s, the 70s, the 60s, sometime before that, you'll probably see p is greater than or less than 0.05, but more recent papers, as of APA 7, I believe, or no, as of APA 6, so the edition before the current edition of APA style, you have to report the full p-value, whether you reject the null or not. Now, this is an example of how you would write up an APA style write-up if you failed to reject the null, which is what we did in our example. If you did reject the null, here I've got another example for you. We're not going to do the full math, but like I've given you, here's the t-value you got, here's your degrees of freedom, here's your critical value. Let's say this is another example. So let's say I wanted to know if lunches made by Tatsu, this anime character, are better than lunches that, like, his homemade lunches, are they better than the lunches you can buy from the konbini, the convenience store? And then I reject the null and I find they are. I might say lunches made by Tatsu were rated as significantly more delicious. So I'm saying they were more delicious. This indicates that it was significant. Even if you don't understand stats, I'm telling you there is a difference. Then lunches bought from the convenience store. So lunches made by Tatsu is one condition. Lunches bought from the convenience store is another. I've told you that my 2 conditions. I've told you my dependent variable, how delicious they were. And I've told you that there was a difference and what that difference was. They were more delicious. And then if you do want to see the stats for nerds, if you don't trust my sentence and want to see my numbers, I did a t-test, so t goes here, with 60 degrees of freedom. The t-value that I calculated was 3.14, and I rejected the null, so p is less than 0.05. The probability that I would have selected this sample of lunches from the population distribution if the null was true is less than 5%. And again, like if you were like actually doing a proper write-up and you'd use a statistical program to calculate this out, you would give me an exact p-value of like p is equal to 0.031, or p is less than 0.001 if it's a really small p-value. So yeah, that's APA style writing up a t-test. So here's our new 6 steps for hypothesis testing, adjusting for doing t-tests as opposed to z-tests. Pretty much the same. There's just a little extra work that we're doing on step 2. Now we've got to estimate our standard deviation and standard error instead of me just giving them to you. Now we actually have to look up our critical value, then assuming it's just the typical one we use for z-tests. And now we're using a slightly different formula to calculate our statistic. Other than that, though, everything's pretty much the same. Now, this isn't the only way you can use a one-sample t-test. So the example that I gave you assumes that you have the population mean, but you don't actually need the population mean to do a one-sample t-test either. You can compare a sample mean to a single number. So the formula for a one-sample t-test is t is equal to a sample mean, minus the population mean over the the sample standard error. But this doesn't actually have to be the population mean. I could also use a single number there. So let's say I wanted to test whether a player significantly to be a regular on the team, to be one of the first people on the court, one of our primary players, you have to score an average of 9 points, or significantly greater than an average of 9 points. I could put my threshold here and test that player's mean points per game and see if it's significantly different than the threshold of 9. That's another thing I could do. Or let's say I want to know if I've created what I think is a cure for depression, which doesn't exist, but let's say I think I've created the cure for depression. And the diagnostic threshold for depression on some measure is 12. I could see if my sample of people with depression, if their average depression levels fell below this threshold of 12, significantly speaking, after I gave them my cure. And that would be another example of a use of a one-sample t-test. It doesn't need to be a population mean. It's just any number that has meaning, whether that's the population mean or whether that's some sort of benchmark or threshold. You can also use it that way. I've used it that way. So that's the one-sample t-test. I'm not done yet. I've got another 10 slides, but I hope that we're doing... How are we feeling? Is everything we following along okay? Anything I can clarify? Anything like that? I hope we're doing all right. Yeah, seems good. Makes sense. Awesome. I'm glad to hear it. Oh, do I have I want to sparkle. No, that's not the right one. I can't tell if I'm sparkling. I'm not sparkling, am I? What have I done? I turned on a toggle and I don't know what it was. No. No. There we go. Now I'm sparkling. This is me displaying my delight. I need to get better about figuring out what all these buttons do. I'm putting my jacket back on. There we go. All right. So now let's talk about effect size. Cohen's d. That was an effect size we talked about. And this was the population Cohen's d. I actually already kind of talked about this on a previous slide today, so oops. The formula for Cohen's d, I think a tier happened when I was filling out a spreadsheet. Yeah, a tier did happen. It was intended to be a sweat drop when I was rigging it, but yeah, you did see that. It could be a tier. It's a very versatile toggle. So, this was the population version. I've already mentioned this, I think, but yeah, if you want to change it into the sample version, we just replace the population standard deviation with the estimated sample standard deviation. That's Cohen's d. I haven't really talked about interpreting Cohen's d yet, though. So what does Cohen's d mean? So that's what the next slide is for. Cohen's d is an effect size. So that means t-test, z-test, they're just telling you yes or no, is there something happening here? Is there a difference between these two numbers? It doesn't tell you how big the difference is. It's like that fire alarm example I used last time. It's like a fire alarm going off. It tells you there is smoke. It doesn't tell you how big the fire is or how big the source of the smoke is or even what the source of the smoke is. The t-test and z-test can only tell you, is there something here, yes or no? It doesn't tell you how much. Cohen's d is the how much or how big. Cohen's d is in units of standard deviation. So a d of 1 means that your treatment group is 1 standard deviation above your control group's mean. So your treatment's group mean is 1 standard deviation above the control group mean. So these are different standard deviation or different Cohen's d's. This, the red distribution here, this is your control. The blue distribution, or purplish distribution, is your treatment. A Cohen's d of 0.2 says there's 0.2 standard deviations worth of distance between the mean of your control group and the mean of your treatment group. This would be considered a pretty small effect. There's not a big impact going on right here. Cohen's d of 0.5, there is half a standard deviation between the mean of your control group and the mean of your treatment group. You can also think of this as your treatment, whatever you did, like what medication you gave them, the therapy you gave them, the training you had them do, moved the mean of the treatment group half a standard deviation away from the control group. This would be considered about, so this is like a small effect. This would be a medium effect size. A Cohen's d of 0.8 would indicate that your treatment group is a full 0.8 of a standard deviation away from, why did I write E? That's medium. From the control group. So your control group and your treatment group are 0.8 of a standard deviation away. This would be considered a large effect. Now, I say small effect, medium effect, large effect. Cohen's standards, the guy who I legitimately did not know that's what Cohen's d was. I'm glad that I'm able to help. Yeah, it's the distance. Well, this is for a 1 sample t-test. The interpretation's a bit different for an independent samples or repeated measures t-test. But it's essentially, I think maybe the more generic way to put it would be, it's the difference between a world where the null is true and what you actually found in units of standard deviation. For a 1 sample t-test, that's just like the difference between like your population mean and the sample mean in units of standard deviation. For like an independent samples t-test, which is what I think biologists mostly use, like comparing 2 independent groups, it would be the distance between a difference of 0 and the difference that you found between your 2 groups in units of standard deviation. It's saying how much bigger was what you found than your null hypothesis, or how different was what you found from the null in units of standard deviation. That's what Cohen's d is. So bigger numbers, bigger things. And yeah, now that Phi's here, this is actually great. I was going to talk about the benchmarks. So Cohen's benchmarks was something like a d of around 0.2 would be considered small. A d of around 0.5 would be considered medium, and a d of around 0.8 would be considered large. And these are kind of standards that like I look at when I'm evaluating how big a Cohen's d is. Phi has informed me, and by reading that bio paper, that paper on the gut biome when I collabed with Phi, I have learned that biology standards for Cohen's d what they would consider a small, a medium, and a large effect is considerably bigger than I in psychology would consider a small, or like Cohen, the guy who invented this. Biology is working on a whole other scale. Like, I think that paper had like a Cohen's d of like 0.9 or something, and I was like, oh, that's a pretty big effect. And Phi was like, what? That's tiny. All d's are valid. Yeah, but yeah, like what counts as a small, a medium, and a large Cohen's d varies not just by like discipline, not like just by like biology versus psychology. It also varies within disciplines. So like in social psychology, which is what I specialize in, we have a lot going on. There's a lot of noise. So a 0.2 Cohen's d is kind of like, that's decent, you know? These Cohen standards are pretty decent for social psychology. If you're talking cognitive psychology, where you have more control, they might expect to see bigger Cohen's d's than this. If you're talking like sociology, where they're looking at the society level, they might be looking at similar like general Cohen's standards. If you're talking like maybe chemistry, maybe? Or like, oh, astrophysics. We were talking about last time astrophysics, or particle physics, sorry. Y'all were mentioning last time that particle physics only counts something as significant if it's 5 standard deviations away. Particle physics is expecting a minimum Cohen's d of 5. It doesn't care about Cohen's d's of less than 5. Based on what y'all taught me last time. So, like, your expectations for what is an impressive or, like, an exciting Cohen's d will vary wildly depending on the type of research you're doing. I think a lot of that is, like, depending on how, like, much control you have over your study, how much, like, error variance you can get rid of, how clean and it is. Don't get out of bed unless it's a t greater than 5. That's my impression of particle physics and particle physicists after last stream. Us in psychology, if we saw a Cohen's d of 5, I think we'd just about faint. I'm trying to think of the biggest Cohen's d I've seen in psychology, and it might have been around 5. I'll have to look. I think I've actually heard of a Cohen's d in psychology of like 8. I'm not sure. I'll need to look. I'll need to look, but like 5 is ridiculously huge as far as a psychologist, especially a social psychologist, is concerned. That is absolutely crazy. We just need a bigger particle collider. We will find the graviton, we swear. I believe in you. I believe in you. I take you at your word. I don't know any better. All right. The other effect size that I want to talk about is R squared. R squared is doing the same thing as Cohen's d in that it's trying to quantify how big of an impact your independent variable had on your dependent variable, but it's going about it in a completely different way. R squared is the amount of variance in your dependent variable that can be explained by your independent variable. Or, as I put it on the slide, the amount of variability that's explained by the treatment, which is, I think that's a lot more abstract than Cohen's d. Cohen's d is just like, how far away did your independent variable push your treatment group? Like, how much did it change your treatment group in units of standard deviation? R squared is like, what does that mean? So let's talk about R squared. And I'm going to use a more concrete example because I think that makes it easier to talk about. If you're a big fan of comics and manga, like me, you will know that different manga have different lengths. Some of them, like might only get like 3 or 4 chapters. Some will get 10, 15 chapters, 30 chapters. I think lately Shonen Jump titles are going between like 120 to 180 chapters on average, the newer ones. And then you'll have things like One Piece, which has like well over, I don't even know how many, well over 1,000 chapters, So different manga have different lengths. There's variability in the number of chapters in a manga. Let's say I knew which magazine was publishing which manga. So if you're unfamiliar with the way that serialized manga work, it's kind of like anthology. Well, not anthologies, but basically it's installments. They once a week or once every 2 weeks or once a month, depending on the magazine, they will release a thing that has a chapter of each manga. So like a magazine might have like 7 manga running at a time, and it releases a volume of the latest chapter of all 7 of those. So say I knew which magazine this manga was being published in. Some of the variance in the length of the manga can be explained by the magazine it's published in. Certain magazines are organized by genre, like there's some magazines that are aimed at young women, some magazines that are aimed at young boys, some that are aimed at older women, some that are aimed at older men, that kind of thing. And different genres of manga have different average lengths. If you want to like hear more about that, I have a live stream VOD from like maybe 2 years ago where I analyzed whether the length of anime differs based on genre, and it does. Shonen tended to be longer. So let's say some of how long a manga ends up running, how many chapters it ends up being, can be predicted by the magazine that it's published in. Here's the formula for R squared. It is the t-value squared divided by the t-value plus the degrees of t-value squared plus the degrees of freedom. And this will spit out a number between 0 and 1. An R squared of 0 indicates that none of the variance is explained by the treatment. There is 0 relationship between the length of a manga and the magazine that it's published in. Nothing. Like, 0 things going on there. An R squared of 1 would indicate 100% of the variance is explained by the treatment. If you're published in Shonen Jump, that explains the exact length of your manga. And this would probably be like, if I knew you were published in Shonen Jump, I know that your manga is going to be exactly 230 chapters long. Every manga in Shonen Jump has the same number of chapters. Every manga in Weekly Shonen Sunday or whatever has exactly the same number of chapters. So if I know which magazine you're published in, I know exactly how many chapters that manga is. Another way of thinking about this, I a lot of times when I'm teaching this to a more general audience, I talk about studying. Different students get different scores on the same exam. And some of that can be explained by how much they study. So that can be explained by things like, R squared of 0 in that case would be studying had no impact on final grade. How much you studied is completely unrelated to your final score. An R squared of 1 would be, if I know how long you studied, like to the minute, I could predict your grade down to the decimal point. There was no other factors in your grade other than studying if R squared is 1. So let's say I have an R squared of 0.33 with this manga example. That would indicate that 33% of the variability in how long a manga is down to the magazine that it was published in. So the magazine that it was published in does have some influence. Some magazines tend to publish longer manga. Others tend to publish shorter manga. But there's other factors as well. 67% of that, I don't know why those differences are there. It could be things like maybe the popularity of the manga, the financial state of the magazine. It could be, well, not the financial state of the magazine, that would be explained, but like 33% is down to which magazine it's published in. The other 67 might be, the health of the person writing the manga, the complexity of the plot, the number of characters, all these types of things. That other 67%, I don't know why these manga are different lengths, but at least 33% of it is down to just sheerly what magazine they were published in. To put it in terms of studying, if R squared for studying, predicting grades is 0.33, that would indicate 33% of the variation in students' grades is down to how much they studied. The other 67%, I don't know. It could be whether they have a background in the subject. It could be how bad their test anxiety is. It could be down to how much sleep they got last night. I don't know what 67% of the differences in scores are down to, but 33% is down to or how much they studied. Yeah, health of the author cries into Togashi. I know. There's so many incredible manga that, drawing manga, especially on a weekly schedule, like Weekly Shonen Jump, that's brutal. That is really bad for your health. It is incredibly detrimental to your health. A lot of mangaka have like serious health issues. It's really not a healthy lifestyle. Like secret Mylan lore. One of my life goals is to publish a graphic novel, and for a long time I really wanted to become a mangaka. Like, I love drawing comics and I really wanted to become a mangaka. But if you look at the type of schedule they're on, that is not sustainable. That will destroy you. Like, that will, you're gonna get carpal tunnel. And then like it's bad. It's rough. So anyway. Okay, so Cohen's D is just how far what you found is from the null hypothesis. How big of an impact did your treatment have on the dependent variable in units of standard deviation? R squared is, okay, how much of the differences in your dependent variable is down to your independent variable? 33% of the differences in my dependent variable is down to my independent variable for an R squared of 0.33. Now let's talk about confidence intervals. I've kind of lumped them under effect sizes, but they're not really an effect size. Confidence intervals are the range of possible values for a population parameter. So, for example, a population mean, or the difference between two population means, or the population standard deviation, given sampling error. And this is an estimate based on samples. So like, this is an estimate based on your sample of the total range of possible values for some population parameter, like the population mean. It's a complicated thing. I could get more into this. It's a bit more complicated than that, but this is intro to stats, right? So we're going to keep it like this. So for a 95% confidence interval, that's more or less saying, kind of oversimplifying, based on the data from our sample, we are 95% confident that the population mean falls between these two numbers. Based on the data from our sample, based on what we've observed in our sample, we have 95% confidence that the true population mean is in this range. Again, oversimplification, but that's roughly what this is getting at. Here's the formula for a 95% confidence interval for a t-test. M is the sample mean. So this is specifically for a one sample t-test. M is the sample mean. T-crit is the critical value that you look up in the t-table. This is the value that you use to decide whether to reject or fail to reject the null. S of M is the standard error of your sample. And you have to do this twice. See this plus or minus here? Let me get my pen. This plus or minus, you have to do this twice to get the upper bound of your confidence interval and the lower bound. So we're pretty sure it's between these two numbers. What's the lower number and what's the higher number? So let's do an example. Let's say I give 16 people cognitive behavioral therapy for depression. I'm sorry, I didn't end up coming up with a manga or anime example for this. We're just going straight psychology. So let's say I give 16 people cognitive behavioral therapy for depression. This is a common treatment for depression. After their treatment, their mean on the Beck Depression Index, BDI-2, this is a common way of measuring depression. Their score is 15, which indicates mild depression, with a standard deviation of 4. So let's figure out the 95% confidence interval. The formula is in the upper right-hand corner. It's your sample mean plus or minus the critical value times the standard error. So that's 15 plus or minus your critical value times the standard error, because our mean is 15. Then we look up the critical value in that t-table. So first we need our degrees of freedom. We have 16 people. Our degrees of freedom is our sample size minus 1. 16 minus 1 is 15. So our degrees of freedom is 15. We go to the 15th row. We go to the column for alpha 0.05. This is a 95% confidence interval, so 0.05. If this was a 90% confidence interval, we would go to alpha of 0.01 or of 0.1 and so on. Did we already talk about degrees of freedom? Yeah. Yeah, we already talked about degrees of freedom. Degrees of freedom is your sample size minus 1. It's always something I have to look up before class. Yeah. Yeah, the whole concept behind it is a little fuzzy. Yeah. I kind of, honestly, I didn't go into it in too much depth. I went into why we use it, but not too much. Not too much about why we do it that way in particular. I'm sorry. All right. So if we look up our t-critical in the t-table, we'll get a t-critical of 2.131. So now we've got 15 plus or minus 2.131 times our standard error. As a reminder, so here's where we're at. The formula for standard error in a sample is your standard deviation over the square root of your sample size. We have our standard deviation, that is 4, divided by the square root of our sample size, which was 16. We had 16 people. 4 divided by the square root of 16 ends up being 4 divided by the square root of 16 is 4. Our standard error is 1. So we calculate all that out. And we end up with a formula that looks like this. 15 plus or minus 2.131 times 1. Of course, 2.131 times 1 is just 2.131. So it's sort of really 15 plus or minus 2.131. We do this twice, first with 15 minus 2.131, and then 15 plus 2.131. And we end up with something looking like this. So 15 minus 2.131 is 12.87. 15 plus 2.131 is 17.13. Here's our 95% confidence interval, and this is the APA way of reporting that. 95% CI for confidence interval is from 12.87 to 17.13. So here's our sample average, 15. And we are fairly confident based on our sampling error and based on the information found in our sample that the true value for people with depression who got cognitive behavioral therapy should be somewhere in this range. Again, oversimplification, but that's kind of roughly what a confidence interval is doing. It's saying, this is what we got from our sample. Based on our sample, we think the real value of people is in this range. Oh, here's the t-table looking up that. Oh boy. We get an explanation of degrees of freedom in physics, but I think that's just for particle in, but even then it's a bit iffy. Yeah. My explanation is more or less we do degrees of freedom because we know that if we don't, we're going to underestimate the variability in the population. But the reason that it's specifically the sample size -1, there's a couple of ways of explaining it. Apparently one of them involves matrix algebra, and I'm not at all confident in my matrix algebra, so I try and avoid it. The other is like, how many, let's say I'm calculating a mean, and I've got the numbers 2, 1, or let's say I've got a sample of like 16 people. Never bothered to question what the freedom and degrees of freedom. I'll take maximum freedom, thank you. Okay, so basically the idea is, let's say I have a sample size of 15 and a mean of 4. Something like that. I can change up to 15 of these 16 individual scores and still get a mean of 4 as long as the last score gets me there, right? Like, I have the freedom to change 15 out of 16 of those individual scores from the sample and still get the same mean. That's what degrees of freedom refers to. That's what the freedom part refers to. I can freely change all but one of the scores and still get the same mean depending on the last score. I can keep the mean of 4 even if I change 15 out of 16 of those scores to whatever I want, as long as the 16th score brings it back to 4. Yeah. I wish I could explain it a bit more than that, but that's largely my understanding of it. That's why it's called that. As long as that final 16th score brings it back to 4, I can change the other 15 freely. Yeah. Yeah. I'm glad you kind of get it. I'll accept this as truth and I'm satisfied. I'm just gonna throw a stats textbook at you because like that's a surface level explanation. There's an iceberg here. Like I've explained the tip of the iceberg. If that's all you want, that's fine, but all right. If you don't want any more, I won't give you any more. That's fine. You're safe. But if you ever want a punishment for a future charity stream, Mylan reads the textbook section on degrees of freedom to 5 for 15 minutes on the most monotone voice they can muster. We can do that. Okay. That would be a pretty good charity, yeah. Though it would be punishing the chat too, so I don't know how they'd feel about that. All right, so here's another one. Let's do a study with this question. We're going to do a one sample t-test with this question. I'm not going to do like the 6 steps of hypothesis testing. We're going to do the quick version, like where we just go as quick as possible. Let's say I have a sample of cats from a population with a population mean of 20 on a softness scale. These cats are 20 on the softness scale. They're very soft. After they are given a kitty spa day, we give them nice pets. We give them many brushes. They just have a lovely, lovely kitty spa day. I find that the sample mean softness of these kitties is 24. And the variance is 64. So let's say I have 4 cats. My sample size is 4. The population mean softness is 20. My cat's mean softness after getting a kitty spa day is 24. And my variance is 64. Let's calculate the estimated standard error and determine whether the sample is sufficient to conclude the treatment has a significant effect. In other words, we're doing a t-test. So, the formula for the t-test is t is equal to sample mean minus the population mean over the standard error. We have the sample mean, it's 24. We have the population mean, that is 20. We don't have the standard error though, so we have to figure that out. So the formula for the standard error, oh, I can't write. The formula for the standard error is the standard deviation over the square root of the sample size. But another way to calculate it that I mentioned when I first taught y'all about the standard error is we could also do it like the square root of the variance over the sample size. Now, because we have the variance, I'm going to use the second version because I'm lazy. So let's start by calculating this. Let's start with our standard error, and that's the first thing it tells us to do anyway. So the standard error is equal to the square root of the variance, which is 64, over the sample size, which was 4. What is 64 divided by 4? Anyone know? 16, correct. Good job. And what's the square root of 16? What could it be? 4, correct. There we go. Our standard error is 4. Now we can calculate our t-test. T is equal to our sample mean minus the population mean over the standard error. And now we have all that information, so we can actually do it. Our sample mean was 24 minus the population mean of 20 over the standard error that we just calculated for. I'm going to erase a little bit to make some room. 24 minus 20 is 4, divided by 4. Our t-value is 1. I think we can already guess where this is going. But just for practice, let's make sure to look up our critical value. To look up our critical value for a t-test, we need our degrees of freedom. Our degrees of freedom is our sample size minus 1. Our sample size is 4. We had 4 cats minus 1. Our degrees of freedom is 3. That means on the t-table, so here's the t-table that we had before. On the t-table, we are going to the third row because we have 3 degrees of freedom. We're still assuming the usual of alpha 0.05 two-tailed test, so we're in the 4th column. Third row, 4th column. Our t critical value is plus or minus 3.182. I know that's kind of blurry and it might be hard to see. I'm sorry. But our critical value is plus or minus 3.182. So t crit equals plus or minus 3.182. So I'm going to do a little erasing again. So close to pi. I know. Oh, we're so close. We could be close. I did have pi hidden earlier on in the lecture, right? That was the... Where did I put it? It was... There's your lovely pi, the t-value for this example. All right. So, here's our distribution. Our cutoff to reject the null is negative 3.182 and positive 3.182. Our t-value needs to be beyond that for us to reject the null. The t-value that we calculated was 1. Do we reject or fail to reject the null? Yeah, we fail to reject the null. You are correct. Unfortunately, we cannot conclude that the kitty spa day made cats any softer. It's too likely that this is just the result of sampling error. It's too likely that I just happened to randomly pick 4 cats with a mean of softness that is that much above the population mean. It's still too likely that this is just a fluke. Here's our APA write-up. There was not a significant difference. So no significant difference. We didn't find a difference in how soft cat's fur was. So how soft cat's fur was, that tells you what our dependent variable was. Between cats that receive the kitty spa treatment and cats in general, there's our independent variable. So not a significant difference tells you there was no effect. How soft the cat's fur was tells you the dependent variable. And then between cats who receive the spa treatment and cats in general tells you the independent variable. Then we have our stats for nerds, people who want numbers. T, we did a t-test. We used the t-distribution on 3 degrees of freedom. So now if they want to check what our critical value, they can use this to go to the t-table, look at the 3rd row. We calculated a t-value of 1. Ouch. And we failed to reject the null. P is greater than 0.05. And again, like if this was like in an actual modern journal article that used APA 6 or APA 7 style, this would be an actual p-value. Like p is equal to like 0.514 or something like that. All right, I got one more thing for us. We're going to do a confidence interval. Oh, I guess I have 2 more things for us. Confidence interval. The formula for a 95% confidence interval is the sample mean plus or minus the t-crit times the standard error. We have 25 scores. We have a sample mean of 72 and a sum of squares of 1,046. So first things first, we have a sample mean, so we've got this, but we don't have t-crit. So let's get our t-critical value. To do that, we need the degrees of freedom. If our sample size is 25, anyone want to tell me what our degrees of freedom are? Right, 24. 25 minus 1, our degrees of freedom are 24. So we can use that to look up our critical value. 24 degrees of freedom, this is a 95% confidence interval, so alpha 0.05. Oh gosh. Yeah, this doesn't zoom in that far. We're gonna have to go to one of the zoomed out t-tables. Oh, no wait, this one does. So degrees of freedom, 24, we're in the 24th row. We're in the 4th column. Our critical value is plus or minus 2.064. Yeah, there's like yeah, I know there's a delay. So that is that's why I'm able to, I know there, yeah. I don't know what I'm doing. But I'm on a PC now. So actually the delay is less than it was. For a very long time, I was streaming from a laptop and the delay was horrendous. So this is an improvement. I am thriving. Oh, this isn't nearly as bad as it used to be. All right, so t-crit. 2 point, I've already forgotten. I've already forgotten what it was. 2.064. 2.064. 2.064. I'm remembering. 2.064. There we go. So now we have our t-crit, but we still don't have our standard error. So our standard error is our standard deviation over the square root of the sample size. But we don't have our standard deviation either. So let's try again. Our standard deviation is the square root of the sum of squares over the degrees of freedom. That's sort of the shortened way to write it. And we have both of those things. We know our degrees of freedom is 24, and our sum of squares is 1046. So that's the square root of the sum of squares, 1046, divided by the degrees of freedom, 24. So the square root of... I'm getting tired, so I'm just going to speed through this. 1046 divided by 24. Ew, I don't like that number. 43.58. I don't like it. It's gross. All right, then we take the square root of that. 43.58, take the square root. That's about 6.60. So the standard deviation is 6.60. Then we can plug that into the standard error formula. So the standard error is equal to the standard deviation, 6.60, divided by the square root of the sample size, which was 25. 6.60 divided by the square root of 25, which is 5. 6.6 divided by 25 is 0.264, I think. I hope I'm doing this right. I am too tired. I'm too tired to really think. My brain is going, oh, it's bad. I'm gonna double check that. Okay. 6 points. That can't be right. That is definitely not right. That is, I think I divided by 25 instead of by 5. See, I told you I'm tired. My brain is all, ah. Yeah. You are correct. 1.32. I would move these streams earlier up in the day, but I'm always tired, so that would change nothing. Okay, now we can calculate our confidence interval. So our standard error is 1.32. I'm going to erase all of this so we have room. I feel comfortable erasing it so quickly because there is a VOD of this. If I was like teaching this in front of a lecture hall, I would try and find something else. Some other way to do this. Okay. So the formula for the 95% confidence interval is the mean plus or minus the standard error times t crit. I think I wrote these two in the opposite order, but the order doesn't matter here. Okay, so let's start plugging stuff in. The mean is 72, plus or minus our standard error, which was 6.60, times our... No, oh my god. Our standard error was 1.32. I am so awake. I am so awake. I'm caffeinated. I actually am caffeinated. The problem is, caffeine doesn't work on me. Okay. Times our t crit, which was 2.064. So first thing we do is we multiply these two together, PEMDAS and all that. 1.32 times 2.064. That gives us 2.72, I think. And if I'm getting stuff wrong, please let me know. With every second that passes, I can feel my brain drying up. So now we do this twice. First, let's get the lower bound of the 95% confidence interval. So the lower number. So that means for 72 minus 2.72. So 72 minus 2.72. That gets us 69.28. So here we go, 69.28. Then we get the upper bound, the bigger number, 72 plus 2.72 should be, I think, 74.72, assuming that I haven't completely lost my mind. 74.72. So there's our 95% confidence interval. We can be, based on our sample and our sampling error, we have 95% confidence that the true population mean is between 69.28 and 74.72. Again, oversimplifying, but more or less that. I have one more slide. One more slide, and then I'm gonna go stare at a wall. I can feel my sanity slipping. I'm so sorry. You deserve better than this. But you have me. Okay. I would like someone, if you have the brain cells to do it right now, which if you don't, I can't blame you. I would be a complete hypocrite to blame you for not having the brain cells. I have no idea how you stream after work. I don't know either. How do I stream after work? Badly. Okay. All right. So I would like to know how increasing your variance affects your standard error, and then how that affects your likelihood of rejecting the null. So if I increase the variance, I increase your variance, what happens to my standard error? Does it go up or does it go down? I'm also going to write the standard error formula too, so you have... Yeah, you didn't even need the standard error formula. It goes up. As your variance goes up, your standard error also goes up. That's because your variance is the top of the standard error equation. I could also write it like this, but either way, as your variability goes up, your standard error also goes up, because your variability is the top of the equation. It's the numerator of your standard error equation. Okay. As your standard error goes up, what happens to your likelihood of rejecting the null? Does it go up or down? Yes, good job, Day. It goes down. How do I know? Well, the formula for the t-test is your sample mean minus the population mean over the standard error. As your standard error, the bottom of this equation increases, your t-value decreases. The smaller your t-value, the less likely you're going to be able to reject the null. Your goal with a t-value is to get beyond a cutoff. You want to get as far from 0 as possible. As your standard error increases, your t-value gets closer to 0. So this is like basically the big thread here is, as the variability goes up, your likelihood of rejecting the null goes down. The more variability you have, the more sampling error you have, the lower the likelihood that you'll be able to reject the null. This is why controls and like internal validity and like keeping as much error out of your study as possible is so important. If you don't eliminate a lot of error, you're not going to be able to find stuff. You're not going to be able to reject the null. So you got to be very careful with your study design. Mm-hmm. Oh my gosh. I'm so tired. I had a full work day and then I came here and then I lectured for nearly 2 hours. Well, less than... I've been on stream longer than that, but thank you all. Any questions, comments, concerns, anything that I can help you with before I disappear into the night? Scary that the variance goes down with the square of the sample size. Oh, yeah. But I mean, it makes sense. The more the variance, some of the variance just comes from experimental error. Like, that's not the only source of variance, but like, one of the major sources of variance is just noise. error, randomness. And the more of the population you have, the bigger your sample size, the less that randomness is going to affect things. The less any one like weird participant is going to have an impact on the larger study, you know? So like it, mathematically speaking and theoretically speaking, it makes sense that the variance goes down a lot the bigger the sample size you have, generally speaking. Unless like increasing your sample size also decreases the quality of your data, like use bots. Also more interesting than my earlier lecture on statistical mechanics, which was just last time in thermodynamics than 2 hours. I'm glad. I cannot even imagine what that would be like. I imagine sitting in that class and my eyes just glazing over, just like kind of deal. Oh, I'm tired. I'm gonna I've been talking this whole time with no mic. Yeah, I will see you on Saturday. I said I was going to see you on Monday. I will see you on Saturday. Z, Any, DV stream. Oops. It looks like I lost all of you, but yeah, I'll see you on Saturday, and then I'll see you on Monday for the next lecture. But I hope that I'll see you Saturday. Take care, everyone. Bye. Scuff. It's fine. It's fine.